Hello everyone, I am Dr. Sudhan Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University. And in our previous session, integration 1, we discussed about different techniques of performing integration. Likewise, we did integration by substitution, how to integrate partial functions using partial functions. Apart from this, we also learned how to perform integration by parts. We had also solved all the cases of transforming an a rational function into its equivalent partial functions. Now we are going to extend our discussion towards the simple application of integral calculus. And in this session, we are going to understand what do we understand by the definite integral and how to use this concept of definite integral to find the area under the curves. Also, we are going to understand how to find the length of the curves. The area under the curve and length of the curves are two of the very fundamental but quite powerful application of integral calculus. Now, to just begin with, we are going to start what do we understand by definite integral. Now, so far as formal understanding is concerned, suppose f is a continuous function defined on an interval ab and f be an antiderivative. We already learned that antiderivative of f means integral of f. So, you can always write that integral of a to b f of x dx can always be written fx a to b, that is equal to f of b minus f of a, which is written over here. So, you are supposed to integrate functions fx with respect to dx, whatever solution turns out to be in the interval a to b. There is a lower limit, there is an upper limit. So, this is the lower limit a and this is the upper limit b. So, substituting the value upper limit minus lower limit, you will get the value of the function in the defined limit a to b, in the defined interval a to b. Likewise, for instance, we are supposed to integrate function x dx in the interval 1 to 2. Now, we know that integral of x to the power n dx is equal to x to the power n plus 1 upon n plus 1. So, using this formula and this equation, you are going to get x square by 2 and which is to be evaluated in the interval 1 to 2. So, in place of x, first substitute first value 2. So, you will get 2 square and then substitute value 1 in place of x, you will get 1 square. So, the entire answer of FB minus FA will turn out to be 2 square minus 1 square whole into 1 by 2, and this turns out to be 3 by 2. So, this is how you got the first answer. Similarly, you can apply the concept to the other equations. Likewise, this integral is to be found 1 by x dx in the interval 2 to 3. We already learned that integral of fx f dash x upon fx is nothing but equal to log of fx. We learned this in our earlier session. Applying the formula, you will get it equal to log of x in the to be evaluated in the interval 2 to 3. So, substituting value of 3 upper limit minus lower limit. So, log of 3 minus log of 2, and we also learn log of b minus log of a is equal to log of b by a. Applying this identity, you will get the answer log of 3 by 2. Similarly, you can solve for integral of e to the power x to be evaluated in the limit 0 to 2. Since integral of e to the power x is e to the power x only, evaluating in the limit 0 to 2. So, upper limit minus lower limit, that is e to the power 2 minus e to the power 0, turns out to be e square minus 1. And you can apply the same understanding of the formula integral of f dash x over fx dx is equal to log of fx, and you can solve this identity also. There are some of the properties of the definite integral. These properties are very much listed into your self-learning material also. You can go through these properties, and this will help you out to determine the area under the curves, to determine the length of the curve, and to perform different integrations in the simpler manner. The first property says that integral for a to a, that is there is no upper bound and lower bound, then it will turn out to be 0. Obviously, because this will turn, we know that integral of fx dx is equal to, in say in the limit a to b, then it is equal to fx defined in the interval a to b, and this is turning out to be fb minus f of a. And if b is equal to a, if b is equal to a, then it will turn out to be fa into minus fa, and this is nothing but 0. So, this is right hand side equal to 0. Similarly, integral of a to b fx is equal to minus of integral of b to a fx. So, going this direction and you are reversing the direction. So, the polarity will change from positive to negative. So, integral of a to b fx dx is equal to minus of b to a fx dx. Similarly, you can say that if we are replacing the variable from t to u to x, then it hardly matters and all are equivalent. So, integral of a to b ft dt is equal to integral of a to b fu du is equal to integral of a to b fx dx. Similarly, if you break the limit between a and b into the subinterval a to c and c to b, then you can rewrite the integral a to b fx dx is equal to integral a to c fx dx plus integral c to b fx dx, and integral of 0 to a fx dx is equal to 0 to a f of a minus x dx. These the property number 6 and property number 7 requires your attention, which says that if the function is odd function. What is an odd function? Odd function is a function where f of x is equal to minus of f of x, and an even function is a function where f of minus x is equivalent to f of x. So, in case the function f is odd, then minus a to a fx dx is equal to 0, and in case the function is even, then minus a to a fx dx is equal to 2 times of 0 to a fx dx. So, this is very important formula, wherein you are supposed to keep in mind that the function is odd or even. If the function is odd, then minus a to a fx dx turns out to be 0, and if the function is even, that means f of minus x is equal to fx, then integral of minus a to a fx dx turns out to be twice of 0 to a fx dx. So, these are some of the properties you can understand, and you can look into them in your self learning material also. There is an important theorem in order to understand the area under the curve and all other things for the definite integrals, and this theorem is nothing but fundamental theorem of calculus. This fundamental theorem of calculus says that if f is a continuous function defined on a closed and bounded interval a b, where a is the lower limit and b is the upper limit, then integral a to x ft dt, then ax is equal to integral a to x ft dt, where a is the lower limit of the given interval, and the derivative of ax will be nothing but fx for all values of x belonging to the interval a comma b. Now, what do we mean by that? In order to understand, let's read this remark and then we will follow the illustration given over here. So, it is to be noted that in fact, when fx is greater than equal to 0 and ax is equal to a to x ft dt is representing the area bounded by the function y is equal to fx and the x axis within the ordinates a to b. We will understand this when we go through this illustration. We are say given the function fx is equal to x in the interval minus 1 to 3. Now, we the theorem says ax is equal to integral a to x ft dt. So, ax is equal to lower limit is 1. So, this is a. So, 1 to x ft dt. Now, because function fx given is x, so ft will be equal to t only. So, 1 to x t dt. Now, integrating t dt, you will get t square by 2. So, this is t square by 2, which is to be evaluated in the interval 1 to x, which is nothing but 1 upon 2 x square minus 1, substituting x for in place of t and substituting 1 in place of t, you will get 1 by 2 x square minus 1 by 2 into 1 square. So, this is nothing but 1 by 2 x square minus 1. So, now we got a is equal to 1 by 2 x square minus 1. So, what theorem says, if a is equal to integral of a to x fx dx, then derivative of a is nothing but fx. Now, let us check whether this statement is true or not. In order to verify this, we need to differentiate ax. What is ax? We got ax is equal to 1 by 2 of x square minus 1. So, a dash x, what is a dash x to be? 1 by 2 into 2x minus 0. So, 2 will cancel out and this is turning out to be x, and this is very true that a dash x is turning out to be fx. So, if the statement is true that if f be a continuous function defined on a closed bounded interval a to b, then integral a to x ft dt, which is equal to ax, and the derivative of ax will be the function itself, So, that means the integration and differentiation are opposite to one another. Integration is antiderivative and differentiation is anti-integral, and they are related to the area under the curve. How this is related to the area under the curve? Let us go through the illustration. Again, say we are given a function fx is equal to x. So, this is a linear function. So, that means fx is equal to y is equal to fx is equal to x. That means we are having the graph y is equal to x, which is going to be a straight line as shown over here. Now, in this figure, as y is equal to x is a straight line, now in the interval 1 to 4, we need to evaluate. So, this interval 1 to 4, because this is a straight line y is equal to x, this will enclose a trapezium, and the area of the trapezium is half of sum of parallel sides into height into distance between them. So, what is the sum of two parallel sides? What are the parallel sides? AB and CD are the parallel sides. So, sum of the parallel sides into distance between them. What is the distance between them? Distance between them is AC, or you can say AE. Evaluate at any point x, between 1 and 4, at any point x, which is subtending the value f and e onto the curve y is equal to x, then sum of two parallel sides will be AB plus FE, and the distance between the two is A into E. So, half of this is nothing but area of the trapezium ABFE. So, what is AB and what is AE? Because we are having the expression y is equal to x, so at this point x is equal to 1 and we are having a y is equal to x, so this point should also be 1. So, this point should be x only, and what is this gap? This gap should be then x minus 1. So, AB is x, AB is 1 because this is unit distance 1, EF is x and AE is x minus 1. This gap is x minus 1, So, that means the area of the trapezium is expressed in the expression 1 by 2 into 1 plus x into x minus 1, and this is solved to the expression 1 by 2 x square minus 1 square, because we know a square minus b square is equal to a plus b into a minus b. So, 1 plus x into 1 minus x turns out to be 1 square x square minus 1 square, you can say. So, this is the area under the curve as per the geometry concerned. Now, let us apply the fundamental theorem and see what happens. So, as per the fundamental theorem, we solved in our earlier discussion also that when y is equal to x, that means is equal to fx is equal to x, then ax is equal to integral of fx dx, that is integral of x into dx. Now, integral of or you can say ft also. The expression says ax is equal to a to x ft dt. So we are going to solve it for ax is equal to integral of 1 to x into t dt, and this will solve to 1 to x into t square by 2 into t square by 2, 1 to x t square by 2, and this will solve to x square minus 1 by 2. And you see that x square minus 1 by 2 is nothing but integral of 1 to x t dt, and 1 by 2 x square minus 1 is the area of the trapezium. That the area under the curve is represented by the integral. And to check whether the differentiation is opposite of integration or not, let's find the derivative of a dash x, and we find that a dash x, that is d dx of 1 by 2 into x square minus 1, and this will turn out to be 2x by 2, and this is nothing but x, and which is nothing but your fx. So we understood that by this illustration that the area of the trapezium for the area of the trapezium is represented by the integral. So area under the curve is represented by the integral of the function, or the integration represents the area under the curve, and differentiation is opposite of integration. We learned about these two important concepts by this fundamental theorem of calculus. Now we try to evaluate some of the definite integrals. We are given a definite integral 1 to 4 dx into square root of x. Now you can simply write it as 1 to 4 x to the power minus 1 by 2 dx, and applying the formula x to the power n dx to x to the power n plus 1 over n plus 1. So you can say x to the power minus 1 by 2 plus 1 upon minus 1 by 2 plus 1 into from the range 0 to 1 to 4. So you got the expression x to the power 1 by 2 upon 1 by 2 from the range 1 to 4, that is 2 root x to be evaluated from 1 to 4, that is 2 into square root of 4 minus square root of 1, and this turns out to be 2 into 2 minus 1, that is equal to 2, and which is the answer. So we evaluated the definite integral to definite. Solving definite integral and integral are not different, but the thing is we are given a range, we are given an interval wherein we are supposed to check that what is the value of the integral in that particular range. So if we are given say integral from 3 to 1 dx upon x, now we are using the identity f dash x upon fx, dx is equal to log of fx. So this will turn out to be log of x, and log of x in the interval 1 to 3 or 3 to 1. So this will turn out to be log of 1 minus log of 3, and this is nothing but log of 1 by 3, because we are saying log of a minus log of b is equal to log of a by b. So applying this identity, you will get the expression log 1 minus log 3 is equal to log of 1 by 3. Now we are going to apply the important formulas which we learned in our earlier session, that integral of dx upon x square minus a square is equal to 1 over 2a log x plus a upon x minus a plus c. Now given integral over here is 2 to 4, from the range 2 to 4 we are supposed to integrate the function dx upon 2 x square minus 3 and minus 9. Now this can be written as 3 square. So that means a value is 3, a is equal to 3. So that means we can write 2 to 4 dx upon x square minus 3 square and apply the formula number 1. So by formula number 1, it is 1 over 2a log of x plus a upon x minus a, and that is to be evaluated, and we know that a is equal to 3. So this is to be a is equal to be 3. So this is 2 into 3. So that is 1 over 6. Now it is to be evaluated in the range 2 to 4. So substituting value 4 for 4 and 2, you will get log of 7, because a is equal to 3. So this will be simplified to log of x plus 3 upon x minus 3. So 4 plus 3 is 7 and 4 minus 3 is 1. So this is log 7 minus log 5. 2 plus 3 is 5 and 2 minus 3 minus 1. Yes, log of 7 minus log of 5. So this is turning out to be 1 by 6 log of 7 by 5. I hope you understood how we got the value of the function in the defined limit 2 to 4 by using the definite integration. Now, important concept is area under the curve. As we had already learned in our earlier slide that we were given a straight line function y is equal to x, and we understood that the area of the trapezium is represented by the area by the integral of the function fx dx, where fx was x only. So we need to formally state what is the area under the curve. Suppose f is continuous and fx is greater than equal to 0 for all values of x belonging to a and b, belonging to the interval a b, then area bounded by the function y is equal to fx and the x-axis, that is the ordinates between x equal to a and x equal to b, is given by the integral a to b fx dx, which is represented over here into the figure. And we already learned that we were having the function fx, wherein we had solved the case for y is equal to x, and in the interval 1 to 4 for any value of x, we wrote the expression 1 to 4 fx dx, which is nothing but a definite integral. And we found that it is the area, area of the trapezium which is equivalent of that integral. And this is shown over here that y is equal to fx is a random general curve, then the area under the curve is a to b fx dx. Similarly, we can apply this concept to find the area between the two curves. Say f and g be two continuous functions defined in an interval a b, such that fx is greater than gx always for all the values of x belonging to the interval a b. Then area bounded by y is equal to fx and y is equal to gx, and the ordinates x is equal to a and x is equal to b will be given by a to b f of x minus g of x dx. So geometrically this is shown over here that y is equal to gx is say one function and y is equal to fx is say another function, and fx is always greater than gx. So the area between the curves, will be given by integral of a to b fx minus gx dx. What do we mean by these expressions, these statements? We will learn in a better way when we are going to solve some of the numericals. Likewise, over here, we are supposed to find the area bounded by the x-axis and y is equal to 2x minus 3. So the function given to us fx is equal to 2x minus 3, and it is to be evaluated in the interval 2 to 5. So we transform this given statement into the equivalent definite integral of 2 to 5 2x minus 3 into dx. Now applying the simple rule of integration and solving, you will get the answer x square minus 3x 2 to 5 in the range to which it is evaluated. Evaluating in the range, you will get the answer 25 minus 3 into 5 minus 4 minus 6, and it will turn out to be 12 square units. So the area under the curve is nothing but 12 square units. So I hope you understood how we solve this expression. Provided you practice our earlier exercises and whatever content is given in our self-learning material, then you will be able to solve it in a very simple manner. So this is 2 to 5 into 2x dx minus integral of 2 to 5 into 3 dx. So integral of 2 to 5 will turn out of 2x is 2 into x to the power n plus 1 upon n plus 1, and to be evaluated in the interval 2 to 5 minus 3 into x to evaluate it into interval 2 to 5. So, this will cancel out. So, you will get overall expression x square when evaluated in the interval. So, 5 square is 25, 5 square is 25 minus 4 minus, so this is 1 minus 15 minus 6. So, solving this 25 minus 4 is 21 and minus 15 minus 6 is 9 and 21 minus 9 is nothing but 12. So, 12 square units are there and this is what we got, 12 square units. Now, let me solve one more question for you. Over here we are supposed to find the area bounded by the curve y is equal to x square. Now, this is quadratic. So, the curve is to be parabolic and y is equal to x. So, we are given two curves that is fx and gx. So, fx, this is x square curve and this is equal to y is equal to x square curve and this is y is equal to x curve. So, when we draw the line, so we can write that at the point of intersection at the point of intersection y is equal to x square should be equal to x. So, solving this expression, you can find the values of x for which this equation is satisfied. So, let us solve this equation and we find that substituting x square is equal to x, that means minus x is equal to 0, that is x into x minus 1 is equal to 0. That means for x equal to 0 and x equal to 1, this equation will be satisfied. So, one point of intersection will be 0 0 and other point of intersection will be 1 1. So, this is how we got the two values. Now, the area to required under the curve, now the function, because it is the difference area between the two curves. So, that means x minus x square, this function is to be evaluated in the range 0 to 1. So, we need to integrate, perform definite integral of x minus x square dx in the interval 0 to 1. So, performing the integration, you will get 1 over 2 x square minus 1 over 3 x cube. We simply applied the formula integral of x to the power n dx is equal to x to the power n plus 1 over n plus 1, and x is, that is why integral of x square dx turns out to be x cube by 3 and integral of x dx turns out to be x square by 2. So, we got this expression and solving it for the definite integral, that means substituting the value of 1 and 0, you will get 1 by 2 minus 1 by 3, which is turning out to be 1 by 6 square units, and which is this area, area in between the two curves. So, this is 1 by 6 units. I hope you understood how we got the area between the two curves. Now, in order to understand what do we mean by the length of the curve, so say we are having 2 points, point A and point B, which are defined for value A. At this value point A, the function is having some value f A, and at this point some B, the function is having some value f B. So, point A and B are say A f A and B f B, then the length of the curve, this length in between the point A and point B will be given by the integral of A to B square root of 1 plus dy by dx, that is derivative of the function square into dx, which is given by this expression. So, you need to remember this expression to find the length of the curve. That means the length of the curve is equal to integral of A to B, where A and B are the values for the for the ordinate x. So, into square root of 1 plus dy by dx whole square into dx. So, let us find the length of the curve by applying this formula for the function 2 by 3 x to the power 3 by 2 from the range 0 0 to 4 comma 16 by 3. Now, simply we are supposed to find dy by dx. So, what is y? Y is equal to 2 by 3 x to the power 3 by 2. So, d dx of x to the power n is nx to the power n minus 1. Applying this formula, you will get that dy by dx is nothing but 2 by 3 into 3 by 2 into x to the power 1 by 2. So, this solves to x to the power 1 by 2 only. So, we got dy by dx is equal to x to the power 1 by 2. Substituting the value in this formula, you will get the length is equal to integral of 0 to 4, because the x coordinate values are varying from 0 to 4, 0 to 4. So, that is why definite integral values from a to b are 0 to 4. Square root of 1 plus dy by dx. What is dy by dx? Is x to the power 1 by 2 square of dy by dx into dx. So, this will turn out to be integral of 0 to 4 square root of 1 plus x dx. Now, integrating square root of 1 plus x dx, you will get 2 by 3 1 plus x to the power 3 by 2, which is to be evaluated in the range 0 to 4. Substituting the values for 4 and 0s and solving, you will get the answer 2 by 3 into 5 square root 5 minus 1. So, this is the length of the curve from the point 0 0 to 416. So, 0 0 is the point origin and 416 is the point on the curve, and this is the length of the curve from point 0 0 to 416. I hope you understand how to calculate the length of the curve. Again, there is one more numerical over here, wherein the function given to us is 2x plus 3. Simply we need to find dy by dx and substitute it into the formula for the length of the curve, which is given over here, that is a to b integral of a to b square root of 1 plus dy by dx whole square into dx. That means by substituting dy by dx, which turns out to be 2. So, y is equal to 2x plus 3. So, and derivative, that is dy by dx, is turning out to be only 2. So, square of 2 square is nothing but 4. So, using this in the formula, you can write this expression as 1 to 2, because in the range, in the figure, the value of x is 1 and other value of x is 2. So, you can write it as square root of 1 plus 4 dx, that is square root of 5 dx, that is square root of 5x, to be evaluated in the range 1 to 2. You will get the answer 2 root 5 minus square root of 5, that is equal to square root of 5. So, this is the answer, and this is the length of the curve for y is equal to 2x plus 3 in the interval 1 to 2, that is 1 to 2. This is value 1, this is 2. So, this is x axis. So, after going through this session, I hope you understood what do we mean by definite integral, how to find the area under the curve, and apart from this, area between the two curves. Also, we learned about how to calculate the length of the curves, and ample number of numericals are solved, and try to solve more numericals to have better understanding. Thank you very much.